Okay, let's solve this integral from 0 to 1 x times the floor function of 1 over x dx. I want to make a little note here. Depending on the literature you use, the floor function can have a different notation. Notations most commonly used are this one in the square brackets 1 over x, like we have in this case, or the other notation is 1 over x, but in this lower part of the squared brackets. Of course, the ceiling function would be notated as the upper part of the square brackets of 1 over x, and you can write the ceiling function as a floor function of 1 over x and then add 1 to it. Now, when it comes to solving an actual integral from 0 to 1x, the floor function of 1 over x dx, many students just cancel out x and 1 over x, and then by cancelling out, they get integral from 0 to 1 dx, which is x in the borders from 0 to 1, which is only 1. And of course, this is wrong. 1 over x is an argument of the floor function. You cannot cancel out something which multiplies a function with the argument of that function. So this is completely wrong. A proper way to solve an integral from 0 to 1 x times a floor function of 1 over x dx is as follows. We're going to use a substitution that t is equal to 1 over x, and then we get that the differential of t is equal to negative 1 over x squared, the differential of x. Well, this is equal to negative 1 over x and then entire part squared, the differential of x, and that is equal to negative t squared dx. From that, we get that negative differential of t divided by t squared is equal to a differential of x. Now, for the borders of this integral, we have from 0 to 1. We have a division in this part 1 over x, and the division by 0 is not possible. So that means that we have an improper integral. For the lower border of an integral, we have that x approaches 0 from the side of positive numbers. As t is equal 1 over x, when x approaches 0 from the positive side, t is going to approach infinity from the positive side. Now for x, which is equal to 1, we have that t is equal to 1 divided by x, and that is going to give us only 1. Then our integral, which we have started from, becomes an integral. Lower border is going to be positive infinity, and the upper border is going to be 1. And when we use the substitution, we get 1 over t times the floor function of t times negative 1 over t squared, differential of t. We can use this minus sign here to flip the borders. So we have from 1 to positive infinity integral, and that is going to give us 1 over t cubed times the floor function of t, differential of t. We can now deal with this improper integral by using limits. So this is a limit when m approaches infinity from the side of positive numbers. Integral from 1 to m, 1 divided by t cubed times the floor function of t, differential of t. Now m is a positive real number. As the limit exists for every positive real number, then it exists for natural numbers. Now this is the way we can simplify the problem by looking at number m as a natural number. Now that is useful because we can split an integral as the sum of natural numbers. So we get this to be equal limit when m approaches infinity from the side of positive numbers, sum where k goes from 1 to m minus 1, integral from k to k plus 1, 1 over t cubed, floor function of t differential of t. So the problem which we have to solve now is a limit when m approaches infinity from the side of positive numbers. Sum from k goes from 1 to m minus 1, integral of k to k plus 1 divided by t cubed, floor function of t differential of t. Now the graph of the floor function looks like this. We have the Descartes coordinate system. We have the origin and the numbers 1, 2, and so on. We have -1, -2, and -3 on this part. -1, -2, -3 on this part, and 1, 2, 3, and so on this part. This is the y-axis, this is the x-axis. Now, from 0 to 1, the floor function is going to take values from 0 to 1, but not including number 1. Then from this part right here, from 1 to, it is going to take the number 1. Now for the input from 1 to 2, the floor function is going to take number 1 and it is going to approach the dot 2. Dot 2 is going to take the value 2, and all numbers higher than number 2 are going to have images which are number 2. And of course, this is where number 3 is. So when we take a look from the k to k plus 1 interval, the k is going to have an image at number k, which is this dot right here, and everything to the k plus 1 is going to have an image at k, except the k plus 1. K plus 1 is going to have an image at the number k plus 1. So integrals go respectful of the variable t from k to k plus 1, and on the interval from k to k plus 1, which is this interval, the floor function is going to take the value of k. So this is equal to k. This is then equal to a limit when m approaches infinity from the side of positive numbers, sum where k goes from 1 to m minus 1, k times an integral from k to k plus 1, t to the power -3 differential of t. And that is equal to a limit when m approaches infinity from the positive side, sum where k goes from 1 to m minus 1, k times t to the power -2 divided by -2, and this is going to be in the borders where t goes from k to k plus 1. So this is then equal to a limit when m approaches infinity from the side of positive numbers. 1/2 we are going to take outside of the sum. Sum is going to be from k is equal 1 to m minus 1. We are left with minus k times, and in brackets we have 1 divided by k plus 1 squared minus 1 divided by k squared. We can use this minus to flip the values inside the brackets. So we get limit when m approaches infinity from the positive side, 1/2 of the sum where k goes from 1 to m minus 1, k times 1 divided by k squared minus 1 over k plus 1 squared. And we can write that as a limit when m approaches infinity from the positive side of the 1/2, the sum k goes from 1 to m minus 1, k divided by k squared minus k divided by k plus 1 squared. This is now going to be equal to a limit when m approaches infinity from the positive side, 1/2 of the 1 divided by 1 squared minus 1 divided by 2 squared plus 2 divided by 2 squared minus 2 divided by 3 squared plus 3 divided by 3 squared minus 3 divided by 4 squared plus 4 divided by 4 squared minus 4 divided by 5 squared plus and so on, plus m minus 2 divided by m minus 2 squared minus m minus 2 divided by m minus 1 squared plus m minus 1 divided by m minus 1 squared minus m minus 1 divided by m squared. Now we can use the telescoping trick and we get that this is equal to a limit when m approaches infinity from the positive side of 1/2, and in brackets we have 1 divided by 1 squared, and this is where we are going to use the telescopic approach. So we get plus 1 divided by 2 squared plus, again using the telescopic approach, 1 divided by 3 squared, and of course 1 divided by 4 squared, and so on. The last term is going to be 1 divided by m minus 1 squared. We get it from this point right here, and we are going to rewrite minus m minus 1 divided by m squared. So this is then equal to a limit when m approaches infinity from the positive side of 1/2, we have the sum where k goes from 1 to n minus 1, 1 divided by n squared, minus m minus 1 divided by m squared. Now we can distribute the limit because both of these are convergent. I have a calculus lecture on various criteria of the convergence of series of real numbers here on the channel, and that lecture is linked below in the description of this video, so I urge you to go and watch that. So this is then equal to 1/2 the limit when m approaches infinity from the positive side of sum k goes from 1 to n minus 1, 1 divided by n squared, m minus 1, and of course minus 1/2 the limit from m minus 1 divided by m squared. In the numerator we have m, of course m approaches infinity from the positive side. In the numerator we have m minus 1, so the degree of m is 1 here. And in the denominator we have m squared, the degree is 2. So this entire part is going to approach 0 when m approaches infinity. So this is only equal to 1/2, and we can do this as the sum where k goes from 1, and the limit we can put up here as the positive infinity of 1 divided by n squared. So this is then equal to 1/2, and this sum is equal to p squared divided by 6, which is finally going to give us the result of p squared divided by 12. Now if you want to see one more amazing integral which students have a lot of problems with, I suggest that you watch this video next. Please like, share and subscribe to the channel. I'm looking forward to reading your comments.